Good afternoon, Professor.
Hi.
Hello, Professor.
So last lecture, I introduced this new way of looking at orbits using measures, right, if you remember. So we have a metric space and we have a map of a metric space. And then I defined this sequence of measures mu n by some initial condition, given as the average of the Dirac deltas along the orbit. Any questions from last time? So what we were interested in was the problem of the convergence. Remember, I spent quite a bit of time last lecture. I really, most of the lecture was really just to familiarize, to get a feeling for what this means, because it's quite subtle. So I encourage you to think carefully about the things I discussed last time, just to get a better idea of what it means. In particular, I talked about the fact that this sequence of probability measures may not converge to some probability measure. If it does not converge, it is in some sense a counterintuitive situation. And then I described, therefore, the fact that our goal is to perhaps show that in most dynamical systems this does converge. And perhaps there might be many initial conditions, or almost every initial condition, or many initial conditions may converge to the same measure. So we're interested in the problem of this convergence, right? Does this converge to some measure? This kind of the problem. And it's a difficult problem if we tackle it just by looking at specific orbits. As we saw last time, we can easily construct, in some cases, like in 10x mod 1, we can easily construct orbits in which this does not converge. And if it does converge, it's not clear what it should converge to necessarily. So the approach we're going to take, which turns out to be a very useful approach, is going to be to start by noticing that if this sequence converges to a measure mu, then mu has some very special properties. So in some sense, we're going to say, okay, which kind of measures mu can be the limit of some sequence? We're going to approach the problem in some sense from the opposite direction. Rather than starting with an initial condition and asking whether it converges, we're going to look at which kind of measures can this converge to. And so we're going to prove a theorem, okay, that says that if f is continuous, so if f is continuous, then any limit measure mu of the sequence of this sequence, right, for any initial condition has a property that we call f invariant, which I will define in a moment. So this measure mu has the property of being f invariant, and what this means is that the measure of the pre-image of any set A is exactly equal to the measure of A for all measurable sets A. So since we're in a metric space, we we will be talking about the Borel sigma algebras and Borel measures always. So this is not an immediately intuitive property. I will spend some time to familiarize ourselves and to give some examples. But what I want to emphasize here, first of all, is that this gives you a condition that needs to be satisfied by a measure if this measure is going to be some limit point of this. And therefore, we're going to, if we're looking for measures to which this can converge to, even more if we're looking for physical measures to which lots of points converge to, then it is natural to look inside, to look at invariant measures, because if this is going to converge, it's going to be an invariant measure. Okay? So the natural question also that would come from here, okay, can we also go backwards, right? Our original problem was, what does this converge to? So in some sense, ideally, what would be nice to say is, okay, if I have certain properties on a measure, then there are points that converge to this, okay? And indeed, we will, between this lecture and the next lecture, we will be able to arrive at a very powerful statement that gives us conditions on the measure. It's a little bit more than invariant. We need invariant plus some other conditions, but this will guarantee that, that there exist some points whose averages, whose Dirac delta averages converge to mu. And we will even get some conditions to show in some cases this invariant measure is actually a physical measure as well. Okay, so this is the path, the approach we're going to take. But the first motivation for this definition is that this is a property shared by these, all the limit measures. So we should start with some examples to try to get a feeling of what this means. So first of all, let me just draw a schematic diagram here. So if this is our space X, right? So we have a measure. We have a measure on our space, some probability measure. Remember, this is our kilogram of sand that is somehow distributed in this way. It can be either sitting on a single point, or it can be Lebesgue measure on the interval or the real line, whatever. It can be spread out in some way. So what we're saying, and then we have a map. So we have a map here, f from x to x, and then we have a measure. Right? Now we take a set A, and then we look at the pre-image of A. So I think I mentioned at the beginning, if not, I will mention it now, that this notation does not necessarily imply that f is invertible, right? So even if f is not invertible, what I mean by f minus 1 of A is simply the set of pre-images. This is the set of points x in X, such that f of x belongs to A, right? So the map might not be invertible, but certainly A has some pre-images, so some points that map to A. F minus 1 of A is some set. So under F, all these points map to A. And this condition says that the measure of the pre-images should be equal to the measure of A. So notice that if F is invertible, then this is the same thing as saying, so if F is invertible, we could write f of the measure of the image of A equals A. This would be exactly equivalent to that, right? If f is invertible, then it's a bijection, then saying that the measure of A and the preimage of A is exactly the same as saying that the image of some set is equal to the, sorry, that the measure of one set is equal to the measure of the image. But if f is not invertible, then the two are different, and we will see some example in a moment that shows why this is the correct definition. If you want to, if you were starting with some definition, you'd maybe say, okay, I want the measure to be preserved under forward iteration, but this is the natural condition. Okay, so obvious examples. Let's take the Dirac delta on some point. So suppose mu is just the Dirac delta on some point x. So is this measure invariant? We have some map. So how do we check whether the measure is invariant? Well, suppose we take a set A and its pre-image, neither A nor its pre-image contain delta x, okay? Then in this case we have that the measure of A is equal to 0 and the measure of f minus 1 of A is equal to 0. So this is not a problem. But suppose that the measure of A, suppose that the set A does not contain x, and suppose that the measure, that this set, sorry, the set f minus 1 of A contains x.
X must be a fixed point.
That's right, that's right. So if this happened, okay, then this measure would not be invariant, okay? And this would mean that the image of x lies in here, right? So, whereas if as Milmukshin says, if x is a fixed point, then this picture cannot happen, right? So if x equals p is a fixed point, then you can easily show, right, that if you take a set A that does not contain a fixed point, so if P does not belong to the set A, then this implies that, so if A does not belong here, then this implies that P also does not belong to f minus 1 of A, right? Because, so f minus 1 of A would be here, because if f minus 1 of A contained P, then the image of f minus 1 of A, by definition, f of f minus 1 of A is equal to A would also contain P. Okay, so this looking at all these all these cases carefully is something that is better that you do at home. So I will put this as an exercise to do that, but it's fairly easy to see that the conclusion is that mu, so mu equals delta of x is invariant if and only if x is a fixed point. And then you can easily generalize this again. And again, I will not do the whole argument because it's best really that you think about it carefully. If you have a periodic orbit, P1, P2, P3, okay, then if you have a periodic orbit, so if you have P is equal to P1 up to Pk, okay, periodic orbit with minimal period k, then you can see that you can define a measure mu, which gives exactly measure 1 over k delta P1 plus 1 over k delta Pk, right? So you put equal amounts of measure on each one, and then this is periodic. This is a invariant. Whereas if you put a measure that is sitting where you put like half the measure on one point and then you distribute the measure in not equal ways, then it will not be invariant. Because of course, the pre-images of these periodic points are each other, okay? So when you take the pre-image of some set, if this set is just one point of the periodic orbit itself, then its pre-image must have the same measure as that point, and so on. Okay, so you get an invariant measure on this periodic point. Another simple example is suppose that f x to x is the identity. Okay, remember this is always a good example. So what measures are invariant for the identity map? For the identity map, we have that f minus 1 of a is always equal to a. Right? It's the identity map. So the identity map is also the inverse of the identity map is also the identity map. So every set is invariant. This actual set is invariant. So every measure is invariant, right? Because it doesn't matter what measure you put on here. You take our set X, we take some measure, we take a set A, this A will have some measure. For this, F minus A, the pre-image of A is just A itself, so it clearly has the same, that measure. So every probability measure on X is F invariant. In this case, it's kind of trivial. Okay, so now as we look at some slightly more sophisticated examples, there's a little bit of a technical problem to do with the fact that, so what I want to look at is the map. Let's look at our favorite map, f of x equals kx mod 1, our favorite class of maps, right, where k is an integer and k is greater than or equal to 2. So for example, for k equals 2, we have f of x equals 2x mod 1. Now in this case, it's useful to draw the graph. So we want a set A, and we want to look at the pre-image of the set A. So first of all, we know lots of invariant measures in here, right? So there's lots of invariant measures we immediately know that are here. Which invariant measures exist in this system? Correspond to some of these measures that we've seen here. So all the ones on periodic points, periodic orbits, right? We know that this map here has a dense set of periodic orbits. Remember, we looked at this class of examples. So there's lots and lots of periodic points here. And on each of these periodic points, we have an invariant measure. But also, we will show that Lebesgue measure is also invariant for this. For this map. Indeed, of course, if you take a set A, so if we take an interval A, and we look at the pre-image of A, the pre-image has two components. And even though I did not draw them correctly because they should have exactly the same length, right? So it's clear that because the slope here is 2, this is 2x mod 1, then these intervals get stretched twice the size when they map onto A. So each one of these is exactly half the length of A, and so the union of the two has exactly the same length of A. And you can see this, that for any interval you take, it will have exactly two components. Both of them will have exactly half the measure. So the union of these will have exactly the same measure. So the slightly technical issue that I wanted to mention before is that in the definition of invariance, in principle, we should check that for any Borel measurable set, this holds, right? Not just for intervals. Now, Borel measurable sets can be very strange. I mean, in this case, it's piecewise affine, so you could possibly argue that it's clear that this holds. But strictly speaking, the way around this, which I'm not going to formalize or spend too much time on it because it's really a technical issue, but I want to mention it, is that it is enough to check invariance on an algebra of subsets which generates the Borel sigma algebra. Right? I don't know if you did in the real analysis course, you did the Kolmogorov extension theorem. I'm sure Milmokshin knows it in his sleep, right? But if the measures are uniquely defined by their values on the algebra that generates the sigma algebra. In the case of intervals, this means that if you have a measure and you know the value of that measure on all subintervals on 0, 1, then that uniquely defines the measure. Okay, and it's possible to show that this means that if you check invariance for intervals, then this implies invariance for all measurable sets. Okay, it's a small technical point, but it's worth mentioning, although we don't need to go into the details of it. So this to explain how you can, it is sufficient in this and in other cases to check the invariance for intervals. Okay, so this is an interesting example in which we have many invariant measures. So the other ones that I did is just fixed points, periodic points in a general setting. This is the first actual particular examples. We also have, perhaps I should have, I forgot, maybe I wanted to do that example first. For circle rotations, x plus alpha mod 1, right? Remember circle rotations. Then for circle rotations, we have here the circle. This is just a translation. Remember, x goes to x plus alpha. So this is a translation or rotation of the circle. And also here, it's easy to see. If you remember, we had two different cases. When alpha is rational, then every point is either fixed or periodic. Every point is periodic. So we have all these measures on the periodic orbits. But we also have Lebesgue measure is also invariant in this case, clearly, right? Because this is an invertible map. If you take a set A here and you translate it backwards to f minus 1 of A, is just the rotation of this arc. So clearly the measure of f minus 1 of A is equal to the measure of A. And again, we can check on the intervals and we get that Lebesgue measure is invariant. Right? So if alpha is rational, then you have the coexistence of the invariance of Lebesgue measure, also the invariance of all the various measures on the periodic orbit. So in general, you have lots and lots of invariant measures. This is something that I want to emphasize. Sometimes you do, sometimes you don't. For example, if alpha is irrational, if you remember, when alpha is irrational, then topologically every orbit is dense. And it can be shown that in that case, Lebesgue measure is the unique invariant measure for this system. We're not going to prove this because we don't have enough time to do this in the course. But for the circle rotations, you have these situations in which you have just Lebesgue measure is the unique invariant measure. Okay? And in these cases here, so let me call this actually example 4. This is example 5. In this case, also we have the coexistence of lots of measures. In fact, in this case, there's even more measures, which we're going to see probably next week, which are not on periodic points, which are not Lebesgue measure. They're sitting on some interesting zero measure set, which has a very rich dynamics anyway. So there's a very, very rich world. The family, as we shall see, of invariant measures can be a huge space of measures, even for simple dynamical systems like this. And before we start to go through the theory, let's just look at some other examples, which I will leave as some exercise. Notice that if you you don't need to take this, so you can do the same argument for 3x mod 1, 4x mod 1, it's easy. You just will have a certain, for 10x mod 1, you will get 10 pre-images. Each one is 10 times smaller. But what is more interesting is that they do not have to have the same size, right? So also, if your map is like this, piecewise affine, like this, and then you take some subinterval, okay, and this has a small pre-image here and a big pre-image here, okay, and then if this is some point Q here, you can actually calculate the slope of this and the slope of this are not independent of each other. As you change Q, both slopes change, and you will be able to check, I will put it as an exercise, that the sum of these lengths is exactly A, okay? And not only that, but even if you have an infinite branch piecewise affine map, Lebesgue measure is still invariant even for that infinite piecewise affine full branch map. Okay, that requires a little step, a little thinking more, but it's a very interesting result. Okay, so this gives our first set of examples of invariant measures. So now let's start working towards our theorem, right? Our theorem is that we want to show that if you have if f is continuous and the measure mu arises this limit, then it satisfies this invariance property. So how are we going to do that? Okay, so we need to introduce a little bit of notation, and I'm going to use the notation M, the space of all probability measures X. Then I'm going to use this notation MF to be the space of all measures in M which are F invariant. Okay, so this is clearly a subset of this. So we're assuming that we're given some map on some metric space. So we don't know whether this is non-empty even or not. Right? We know that this is non-empty. Why do we know that the set of probability measures is non-empty?
Thus, Dirac measure is also delta H.
That's right. So as long as X is non-empty, right? So as long as X is non-empty, as long as it contains at least one point, you can always define the Dirac delta measure on that point. That's a probability measure in your space, right? So as long as X is non-empty, the space of probability measures is always non-empty. The space of invariant measures is on the other hand, is non-trivial whether this is non-empty. In fact, we shall see an example in a second where it may be empty. I'm not sure whether to give you this example now. So. Okay, I will give some example in a second, but we would like to show that it's non-empty. Well, maybe let me give it now. So, okay, let me state, let me state the theorem first. So, we have here this map f x to x, and this induces a map. So we define a new map, which we call f star, which is a map from the space of probability measures to itself. And it's defined in the following way. So we take a measure mu, it maps to a measure which we call f star of mu, which is the image of this map. And this is defined in the following way. If you define f star mu of some measurable set A, this is by definition the measure mu of f minus 1 of A. This is called the f star. It's called, so f star mu is called the push forward So what is this? What is the meaning of this here? We have our space X. We have our map F. We have a measure mu that gives measure to every Borel subset of this. Now, we're not worried about whether mu is invariant or not. We're just now defining, use this map, we're going to define a new measure which says the following. We would take a set A. Okay? We know what the mu measure of the set A, but we not care about that. We want to define what it means, what the measure of A is under this new measure. And the way, what I do is I look at the pre-image of A under F, and I look at the measure mu of this pre-image, and I define that value to be the measure of the set A for this new measure. Okay, it's not a completely intuitive process, but it has a very interesting feature we will see, and that if S is invariant, so notice that mu is F invariant. What do we get if mu happened to be invariant? Maybe we didn't know that, but if mu happened to be invariant, then by the definition of invariance, the measure mu of A and the measure mu of F minus 1 of A are the same. That's what it means for the measure to be invariant, for every Borel measurable subset, right? So that means that if mu is invariant, then the measure mu of F minus 1 of A is the same as the measure mu of A. So this means that F star mu of A is equal to the measure mu of A for every subset, which means that F star mu is actually equal to mu. If and only if, right? This is equivalent. So we have defined an interesting kind of map on the space of probability measure, which has this property that it fixes all the invariant measure, right? This map, if you take a map that is invariant, then it's a fixed point for this push forward F star. So we have, in some sense, we have reduced the problem of finding invariant measures to the problem of finding a fixed point for this map from the space of measures to itself. Now, when I say it this way, it will be tempting. As you know, there are many so-called fixed point theorems. There are many theorems that give you conditions for when you have a fixed point, but like the contraction mapping theorem, right? So a lot of these theorems need particular structures either on the space or on the map. Here, in a very general situation, it's not that easy to apply any of these theorems. So we're going to actually use a slightly different approach to solve this problem. So it is indeed a fixed point problem, but we're not going to show the existence of these fixed points just by applying some abstract fixed point result. Instead, we're going to do it in the following way. So first let me make some remark. So we're going to do this. So now we are going to to fix some arbitrary mu0 in the space of probability measures. Then define sequence of measures mu n, which are the averages of fi star 0. So maybe a remark I should have made here is that it's quite easy to see that you can iterate this map. Okay, sorry, maybe I should have made this remark before, is that this is a map from the space of probability measures to itself. So just like what I said right in the very first class, if you have a map from a space to itself, then you can iterate it, right? And then you can define fi star of mu, right? And it's quite easy to see from this definition that in fact fi star mu of A is just equal to mu of f minus I of A, right? So you keep taking preimages. So you take the preimage of this, the preimage of this. So now if you take fi of A and you look at the mu measure of f minus 1, f minus I of A, then that is the definition. Well, that's not the definition, but that corresponds exactly to f iterating this map I times. Okay, so this is what we do here. We're going to take the iterates of this map, and then we're going to prove the following theorem. It says that if f is continuous, f x to x is continuous, then any limit point. So again, we do not know whether this sequence converges or not, but any limit point, any limit measure, mu, okay, such that we have some subsequence converging to mu in the weak topology, is F invariant. So now this is a generalization of the theorem that I wrote right at the beginning, right? So the theorem I wrote at the beginning is that if f is continuous, then any limit measure mu of this sequence here is F invariant. Okay? This sequence is the limits of the Dirac delta averages. Now what is the relation between this and that theorem there? Well, interestingly, if we take mu0, so notice that if mu0 is equal to Dirac delta on some point x0, right, then what is mu1? Okay, well, maybe I will leave this also as an exercise, but it's easy to see that mu1, which is, sorry, that f star of mu0 is exactly equal to delta in x1. Because what is f star of mu0? So f star of mu0, indeed remember that by definition, so f star of mu0 is equal to f star of delta x0, right? F star of delta x0, and this is delta x1, because what does f star of delta x0? So f star of delta x0 of some set A, by definition, right, f star of this measure in a set A is by definition equals to delta x0 of f minus 1 of a. Right? So if we take as our set A the point x1, so if A is equal to the actual point x1, right, which is the image of x0, so we're taking this measure here, and we are measuring just a single point x1, right, then this is by definition is equal to delta x0 in the pre-image of this set. So this is x1, right? And the pre-image of x1 obviously contains x0, right? Because x1 is the image of x0. So this pre-image, if the map is not invertible, this pre-image may contain several points, but it certainly contains x0, right? This set here. And therefore, since this contains x0, then this is equal to 1. Right? So if we take f star of delta x0 and we take the measure of just a single point x1, it will be equal to 1. So this means that f star of delta x0 is exactly the Dirac delta in x1. Any questions? Please ask questions if you get lost at any stage. So what this means is that this theorem that we wrote is just a special case. This is a generalization, right? So here we take any probability measure and we look at the sequence of averages. And if we take as our initial probability measure the Dirac delta in some initial condition x0, then this gives you exactly the sequence. So in general, we have that f I star of delta x0 is exactly delta xi, right? Where xi is the image under fi of x0. So this means that here we take the sequence fi star of delta naught of delta x0 will give you delta xi, so we will get exactly that same average that we had before. So this is the theorem we really want to prove, right? The one we had before is a special case of this. And how are we going to prove this? So it's not actually that difficult. It depends on the crucial way on the following result. Yes, so first I promised that I would say what happened if f is not continuous. Then, okay, wait, so here it says that any limit measure is invariant. Yes, so this holds, this does not hold if f is not continuous. We can have a very simple example of this. So this is false in general if f is not continuous. For example, take f from 0, 1 to 0, 1. We take a simple example. F of x is equal to 1/2 of x if x is in the open interval, a half open interval 0, 1, and is equal to 1 when x is equal to 0. So, yeah, f of 0 is equal to 1. So this is just this map here. This is 0, 1, and this is just standard 1/2 x plus 1, but the image of this is in 1. Right? The image at 0 is in 1. F of 0 is 1. Okay? So then it's clear that if you take any initial condition here, x0, right? If you take the measure mu0, if mu0 is equal to delta of x0, then mu n 1 over n, the sum I equals 0 to n minus 1 of f star I of delta x naught. This is just, as I said, 1 over n, the sum of fi, the sum of delta xi, okay? And then this is clearly converges to delta 0. This converges to the Dirac delta in delta 0, because that's what it does, right? It obviously converges to the Dirac in delta 0. But delta 0 is not a fixed point, right? So delta 0 is not invariant. Delta 0 is not invariant. So we have a situation where we have the sequence of measures. It converges happily to a measure. The measure exists because the interval is the closed interval. 0 exists in the domain of the interval. So it's perfectly legitimate to converge to the Dirac delta in 0, but delta 0 is not invariant. So this is not always true if you remove the continuity assumption. This also, a variation of this also gives a situation where there does not exist any limit, right? So if we just take, I'm not sure if I gave this example in the last lecture or not, actually. Maybe I did. Obviously, if we take the open interval here on 0, and then we don't need to define it. Here, we just define it of f of x equals 1/2 of x, right? Then we get exactly the same thing. We would like it to converge to that. The only possible measure that this can converge to is the Dirac delta in 0, but 0 is not part of our space, so this does not converge, right? And there can be no other invariant measure because there's no other point. Any point you choose, the only possible limit for this is 0. And so this is also an example where there are no invariant measures, right? So this is an example in which we have no invariant measures. So in this theorem, I'm not assuming that any such measure exists. I'm saying if it exists, it's implicit in the notation here, then any limit measure is invariant. So if there exists a limit measure, then it's invariant, okay? The way I've stated this theorem is that way. I hope towards the end of the class, it's quite easy. It follows that if x is compact, then there always exists some limit measure. But in this statement, I'm not assuming anything about the compactness of x, and therefore it's just if there exists a limit measure, then it must be invariant. Okay, so maybe this is a good moment to just take a 5-minute breather, okay, and have a glass of water. So let's meet again at 5 o'clock. Okay, hello everyone. That was a quick 5 minutes for me, probably for you too. Okay, so we're going to prove this theorem here now, which is an important theorem, and we start getting a feeling for the kind of arguments that we use in this kind of situation. And we're going to basically break it. It's quite simple. It's 2 steps. So by assumption, we have this condition here, right? So by assumption, we have some limit point converges to some measure mu. And we're going to show 2 steps. So we will show two steps. One of them, the first one, is that if we now take the sequence f star of mu and j, so we look at this sequence here, right? So here we have the space of measures. This is the space of measures. This is a sequence mu and j converging to mu. We want to show that mu is a fixed point, right? Because we want to show that f is invariant. So we're going to consider the pre-images, the images f star mu and j. And we're going to show that this sequence also converges to mu. So we're going to show that if you take this sequence, this new sequence that you get by applying f star to mu and j, it also converges to mu. That is not enough, but if we show that also f star is continuous, f star has a map from the space of measures to space of measure is continuous, okay? And then if you combine these two properties, so the fact that it's continuous means that f star, so it means that f star of mu and j and I and j converges to f star of mu, right? Actually, this is the continuity. The continuity, you apply the continuity to the sequence, so we're taking the sequence here by this continuity, so maybe I should have written it as a consequence of this. So this implies that f star mu and j converges to f star of mu, right? And therefore, putting these two together, we get that mu is equal to f star of mu, which is the invariance. Okay, so two simple steps, continuity of the measure, and this is the step in which we use, in a crucial way, the continuity of f to show that this push forward is actually continuous in the space of measures. And then this here is a simple calculation. So let's do number one first. So number one is really just a straightforward calculation. I will do a short version of it just to get some ideas. So here we take f star of mu and j. And this here is just equal to f star. So mu and j, by definition, is 1 over n, the sum of f star I of mu 0, I equals 0 to n minus 1, okay? And then it is easy to check that this is kind of linear in the sum, so that you can bring this inside. So this is just 1 over n times the sum I equals 0 to n minus 1.
I think NJ, it was
Sorry?
NJ. NJ.
Ah, yes, thank you. Thank you very much. This is NJ. And this is NJ also. Thank you, yes. NJ, NJ minus 1, Fi plus 1 star of mu 0. Right? So these are all f star I. When you apply f star to the sum of these terms up to time nj, then it's just like applying f star I plus 1, okay, because you iterate this star. And then the way we are going to decompose this is we're going to write this as, okay, it's easy to see that we can write this as 1 over nj, and then we can write this as the sum I equals 0 to to nj minus 1 of fi star mu 0. But then what we're missing is we have a, okay, you can check, you can do the calculation, but what we've got in this sum, we've got a mu 0 too much, so we subtract mu 0, and then we're missing an f star and j of mu 0. Okay, so we've just separated out the terms in that sum, and then we can write this as 1 over nj, the sum I equals 0 to nj minus 1 of fi star mu 0 minus 1 over n mu 0 plus 1 over n f star nj mu 0. And now, as n goes to infinity, as nj goes to infinity, right, this is equal to mu nj, 1 over n, so this is exactly mu nj minus 1 over n mu 0 plus 1 over n f star nj mu 0. And so this mu mj by assumption converges to mu, right? And these, so this is a probability measure, right? This is a sequence of probability measures, and it converges, so the weighting of these goes to 0 because this is a probability measure, this is a probability measure, but you're dividing by n each of these measures, so as n goes to infinity, the mass associated to this is going to 0, the mass associated to this is going to 0, so this is just converging to mu, right, as nj tends to infinity. Sorry. Okay, so that's the first step. So it's just a calculation, really. We've not used anything but the form of the sequence. So we've used, in an important way, the fact that we've defined this particular averages in this way, and it shows that when you take f star of this sequence, you actually converge to exactly the same measure as before. Okay, and then the next point is the continuity, and I will just do a little piece of this. So let's write this as a proposition because this is a general fact. Proposition: if f x to x is continuous, then f star from m to m is also continuous. And this depends on a general lemma which does not actually use any continuity. This is just a general fact, so this holds for any measurable. This holds in any case when this is measurable. We have then for all L1 functions of mu, we have that the integral, so the integral of phi, respect to the measure f star mu, is exactly the same as the integral of phi composed with f with respect to the measure mu. So this is just a general relation to do with Lebesgue integration and the fact that you kind of have a duality here, so that if you there's a relation between integrating a test function with respect to the measure f star of mu is the same thing as integrating this test function where you compose with f with respect to the original measure mu, right? And Let me show it for characteristic functions first, and then there's a standard argument to, which is in the notes, to place it to L1 functions. But for if so, if phi is a characteristic function of some set A, then it's quite easy to see because we have so some measurable set A in X. Then we have this here. What does this mean here? So this is the integral of the characteristic function of A with respect to the measure f star of mu. And as you know, the integral, the Lebesgue integral of a characteristic function is just the measure of the set with respect to this measure, right? So this is just exactly equal to f star of mu of A. And f star of mu of A, by definition, is equal to mu of f minus 1 of A, right? And mu f minus 1 of A, we can write it again as an integral. We can write it as an integral of the characteristic function of this set, f minus 1 of A, with respect to the measure mu. And what does the characteristic, if you think about what this means, the characteristic function of f minus 1 of A is 1 at all the points x which belong to f minus 1 of A, which means all the points x whose images belong to A. So this is exactly equal to the integral of the characteristic function of A composed with f d mu. Right? If you think about it a little bit, then this integrating this characteristic function is exactly the same as composing the characteristic function of A with f. Okay, which is exactly this statement here in the particular case in which phi is the characteristic function of a set. So then there's just a general approximation argument. Extend, I will not write it here as a technical argument, but it's in the notes. Extend 2L1 functions by approximation arguments. Okay, so how do we use this to prove the proposition? Then this is easy. We can prove the proposition. Proof proposition is just now we take, so we want to show that f star is continuous. So how do we show that f star is continuous? Suppose let some sequence, take any sequence converging to some other sequence in M. Okay, to show that it's continuous, we need to show that f star of mu n converges to f star of mu. Then for all continuous functions, for all phi continuous, we have, so this statement is for all phi in L1, but in particular for all phi continuous, we have the integral of phi d of f star mu is equal. Okay, so we apply now this lemma here. This is equal to integral of phi composed with f with respect to d mu. And now, this is where we use the continuity of both phi and, f star d mu n. I'm taking I want to take this in one of these, in each of these measures here, right? So for every n, for all n, I have that this is true. This is mu n, right? So I'm just applying the lemma. And then now here, I have that phi composed with f is a continuous function, right? So this is why I'm choosing phi continuous, and I need to assume here that F is continuous, because then that means that the composition is continuous, and then by the definition of convergence in the weak star topology, I know that this converges to the integral of phi composed with F d mu. Right? So here, this is the definition. This is the fact that mu n converges to mu in weak star topology. And again, I use the same lemma that I just used here to go back to this situation here. So here I get the integral of phi with respect to df star mu. So what I really have is that I have that the integral of phi df star mu n converges to the integral of phi d mu n df star mu, okay, for all phi continuous. And then this is just a, again, to complete the argument formally, you need a little bit of results from function analysis. The fact that the integral is a linear functional. And so what we're saying is that this linear functional, so the measure, the integral is a linear function on the space of measures, and this linear functional coincides, and this convergence holds for all continuous functions, and so this implies that f star, okay, so this implies that f star of mu n converges to f star of mu. So we've assumed that mu n converges to mu, and we conclude that f star of mu n converges to f star of mu, which is the definition of continuity. Okay, so this completes the proof of this theorem. Because we've shown both of these conditions, we've shown that f star mu nj converges to mu. We've shown that f star is continuous, which means that f star of mu nj converges to f star of mu. And therefore, this implies that mu is equal to f star of mu. So we show this theorem, that any limit measure of this sequence is f invariant. So this is the main theorem of today. I just want to finish, however, with a couple of kind of further properties about the space of invariant measure, and also with the condition that is going to guarantee us that this space is indeed non-empty. We have a theorem which is often called the Krill-Bogulubov theorem. Sorry, I'm not saying it, I don't know if I'm pronouncing this exactly right, but Bogulubov theorem, which says that if X is a compact metric space and F is continuous, then space MF of invariant measures is non-empty and compact.
In which topology is it? It is compact.
The
Weak
weak,
star.
always weak star topology. In weak star.
But in weak star, we have general result, Banach-Alaoglu. If we can show it's closed, then clearly it's compact.
Exactly, but what the Banach-Alaoglu theorem says is that the space of probability measures is compact,
Yes.
but this is the space of invariant probability measures.
Yes, showing closedness is enough.
It's basically a consequence of that, but it is crucially, so first of all, the non-emptiness follows exactly as you say from that. So by this general result, by Banach, Alaoglu theorem, M is compact. Okay. So this means that that every sequence has a converging subsequence, right? Which means that we have an invariant measure, right? So this is really the key theorem. I mean, this is, of course, this sits on, deep theorems of function analysis, but by the compactness, this implies that every sequence, so that the sequence mu n has a converging subsequence. Okay, and then by previous theorem, exists a limit point, a limit measure mu, which is invariant. That shows it's non-empty. And the compactness, so I'm not sure if you can deduce the compactness of the invariant measures by a general theorem. To show the compactness, we can use this simple lemma. So let me write it here. So this gives existence. So this implies that MF is non-empty. Now to show compactness, we have a simple lemma. It shows that mu is invariant if and only if. Okay, it's basically, I think, a corollary of what we had before. So phi composed with F mu. So one direction of this is obvious from what we had before, right? Because if phi is invariant, okay, then we have that phi composed with F d mu. Someone's got their microphone not muted. It's a bit of background noise. So you can see that one direction is obvious, because if mu is invariant, right, then the previous lemma says that phi composed with f d mu is equal to phi d f star mu. But if it's invariant, f star mu is equal to mu. So we have this, okay? The other direction is not completely trivial, but so this direction follows by previous, this direction follows by previous position. And to prove this direction, we have that okay, we have a similar argument as before. So here we simply have that if integral, let's say integral of phi d mu is equal to the integral, okay, by assumption, integral of f d mu, and by the previous lemma, this is integral of phi with respect to div f star mu, okay, and then this is for all continuous functions phi, okay, and again we have the same situation that here we have that if the integral of phi d mu is equal to the similar situation, if integral of phi d mu is equal to integral of phi with respect to d f star mu for all continuous functions, that this implies that mu is equal to f star mu. Okay, the two measures are the same because they have the same integral with respect to all continuous functions. Okay, and therefore, okay, this implies the lemma, and therefore, why does this give compactness? So to show compactness, let yes, so let mu n be a sequence in MF, and mu n converging to some measure in M, right? So we want to show that this implies that mu is actually invariant, right? So we have a sequence of measures which are invariant. They converge to some probability measure, right? We need to show that it's invariant. So we have that for any continuous function, so by the lemma before, so for all phi continuous, these things are really better that you do them on your own actually rather than, but anyway, f composed with phi d mu is, yes, is by definition by this convergence here. Since this is continuous, this is equal to the limit of integral of f composed with phi d mu n, and this is equal to the limit of okay, because each mu n is continuous, then we can apply this lemma. So this is the lemma. This is just says that this is the same as phi in d mu n, and therefore this limit by the assumption, this converges to mu. Okay, so we have that sorry, this converges, so the limit of this limit of these integrals is equal to the integral of phi d mu. Sorry, that's what I meant. Okay. And so this means, again, using this lemma, this means that mu is invariant. So this means that mu is invariant. Okay, one just very, very last comment is that in general, so this shows that as long as f is continuous and x is compact, then you always have some invariant measures. And let me just one final comment that does not depend on that. More general, we have that lemma is that MF is convex. Okay, so in other words, if mu and nu are invariant measures, this implies that T mu plus 1 minus T nu is also, this linear combination of measures is invariant. I will leave this as an exercise, but this does not require the assumptions of the Krill-Bogulubov theorem. This is just a general fact. So this shows in particular that in general, if this space contains two measures, then it contains an infinity of invariant measures, right? So really you have a kind of extreme situations where either you just have a system that has a unique invariant measure, like if you have a contraction mapping, then it's just at the delta Dirac at a fixed point, or if you have these irrational circle rotations. But as soon as you have at least two invariant measures, you must have an uncountable infinity of invariant measures, because you can always take all these convex combinations. Okay, this is a very simple exercise, and I will put it in the exercise sheets to do that. Okay, so this is the kind of structure of the set of what we've done today has been to look at we've introduced the concept of invariant measure, and we looked at the structure of the space of invariant measures inside the space of probability measures, right? And we've seen that these invariant measures arise as limits of those averages. That's the most important result of today. And a particular application of that result is that if X is compact and F is continuous, then you always have some invariant measure. We will see, however, that even if we have discontinuous systems, in many, many cases, we still have that this is non-invariant. So this is a general result. And as we saw from this result, if you relax the compactness or the continuity, this might not be true. But in many cases in which X is not compact or the map is not continuous, the conclusions are still actually true. Okay, this is just a general result. Okay, so what we're going to do tomorrow is we're going to study more in detail the properties of invariant measure, and we're moving towards the fact that if you have an invariant measure, the converse of the results we proved today, which is that if you have an invariant measure, then you have many points whose averages, whose Dirac averages converge to that invariant measure, which turns out to be the real deeper motivation for an interest in this concept. Okay, thank you very much for today. Have a very good weekend. It's Easter weekend. I'm not sure what you're going to do about that. I'm not going to do much.
You too.
Okay, bye.
Yep.
Have a good weekend. Bye.
Bye.
Bye.